We now are going to introduce what is called the information form of the Gaussian that involves the parameters lambda and xi that you see on the second equation. Lambda is just the precision matrix as we have seen it before, and xi is sigma minus 1 times mu or lambda times mu. If you simply do those substitutions in the expression for the moments on the top, you get basically the equation on the bottom, and notice the subscript C in the Gaussian symbol to indicate that this is the canonical representation in terms of lambda and xi. So this distribution looks obviously in this form a little bit more complicated and unfamiliar, but hopefully some of the operations with Gaussians will be easier to look at and work with than the moment parameterization with the classical exponential term that we are all familiar with. Okay, so you may ask, well, what type of calculations are we looking? One of those calculations will be to revisit and see if conditional and marginal distributions are looking any more easier informed than the moment parameterization, and of course things such as products of Gaussians that will come often in our course. Can we compute those in an easier way than using the moment parameterization? So hopefully when the next slide comes, we will be able to discuss the form of the conditional distribution of xa given xb, but on an information form. All right, so the formula on the top summarizes again our canonical form, this information form of the Gaussian, and on the second equation I give you the conditional of xa given xb written in terms of the precision matrix lambda and the moment mu. I remind you that we got these equations by partitioning lambda in matrices lambda AA, lambda AB, etc., and partitioning also the vector x in xa and xb and the mean vector in mu A and mu B. So if you do the calculations and in substituting in the form xa given xb the canonical parameters, you get the equation on the bottom, which certainly looks much simpler than the equation, the second equation that you see on the slide. Only one thing that you should pay attention here: the partition of xi in xa and xb follows exactly the same format as the partition of mu A and mu B. So notice what the equation was for the xa. Okay. So the conditional looks in a very nice form, much easier than using the moment parameterization. Now we see the same calculation for the marginal, and you notice in the equation on the bottom the marginal has not benefited much from the information form. It looks a little bit more complicated than the classical equation, where it says, for example, that the mean and the variance of xb's is given directly from the partition of the mean and the variance. So here is another slide showing benefits when you use the information form for the product of two Gaussians. So we have two Gaussians with parameterizations xi1 lambda 1, xi2 lambda 2. When you multiply them, the xi set, and the same is true for the lambdas. This is written for the univariate case, but you can extend the same type of calculation for a multivariate distribution. Of course, the calculation in terms of moments given for the univariate case on the bottom is a little bit more complicated. So when you multiply Gaussians, there is a merit to use the information form than the moment parameterization. All right, so we're ready to talk a little bit about these likelihood calculations and discuss the concept of additive and multiplicative noise. There are lots of examples in the notes that you will consult, so I'm going to be jumping just to give you some of the key ingredients of this type of calculations and relations with things you know, least squares and regularized least squares type of calculations. So I'm going to be talking about point estimates, such as the map estimate, and why it comes out to be identical in spirit to this concept of regularized or penalized, if you like, least squares estimate. So this concept of multiplicative noise is the most familiar that we will play with, but in many areas of applications, multiplicative noise or additive and multiplicative noise simultaneously are very common as well. So what we see here is a summary of the posterior distribution and Bayes rule, and on the numerator you see the probability of the data d given theta. This is the likelihood function, and we treat it not as a probability density but as a function of the parameters theta that we want to compute. We already have seen the maximum likelihood estimate, where we maximize this function to compute an estimate for theta, and so we will try today to do a little bit better by computing the map estimate by maximizing the posterior, hopefully in a few slides down the road. So the maximum likelihood estimate, as we discussed, has some problems, and a good way to see some of the existing problems with MLE estimates is to revisit and remind you how the MLE estimates for the mean and the variance look for a univariate Gaussian. Hopefully you remember these calculations from an earlier lecture. So if you remember, and it's going to be coming up on our next slide, the mean, the MLE estimate for the So we're going to, it seems we had some recording issues. We're going maybe to repeat exactly the same things. Hopefully they don't come twice in the recording. So let's try to change the slide here. So here is the calculation that I was referring to before. You see the MLE estimates for the mean and the variance, and we already have shown that the MLE estimate for the mean is unbiased, is the same as the mean of the distribution from where the data come, but the MLE estimate for the variance is biased simply because the mean that we use to define the sample variance is the MLE estimate. Okay, so this is the sort of a problem that maximum likelihood estimation comes with. Now, a very good demonstration on this issue with the variance in the context of MLE is a picture that is contained in Bishop's PRML book, and I'm going to try to show you this next, and it will give us a very good graphical sort of understanding of what is the issue with